Okay, so here we're looking at problem 4.13 from Peleus. And here we're given a slab waveguide. We're given the indices of the core. N1 is 1.48. The index of the cladding is 1.46. That's N2. And we're given a wavelength of 1.3 microns. And then for parts A and B, we're given that the zigzag angle is 85 degrees. For part A, the zigzag angle is 85 degrees for the TE0 mode, that is the M equals 0 mode. And for part B, the zigzag angle is 85 degrees for the TE2 mode, that is M equals 2. And for both cases, we're supposed to find the waveguide thickness, which makes this zigzag angle equal to this value for these modes. And so I'm going to start off by drawing a picture of an effective versus the ratio d by lambda. Let's see if I can draw it here. Okay, so this is d by lambda starting at 0. And effective ranges from a low of n2 all the way up to n1. And you can also think of this vertical axis as mapping theta zigzag ranging from theta critical all the way up to 90 degrees. Okay? And so the 0th order mode, the M equals 0 mode, has a cutoff at 0, and its curve may look something like this. The M equals 1 mode has a cutoff at some value of delta. The M equals 2 mode has a cutoff at 2 delta. They're evenly spaced, the cutoffs, along this horizontal axis. 3 delta, 4 delta, and the mode plot looks like this. And so what this does is, for a given ratio of d over lambda, it allows us to read not only how many modes there are, but what their effective indices are. And we know that the relationship between the effective index and the zigzag angle is fixed, and so that allows us to convert between them. So basically what we're doing here is, given this zigzag angle, okay, we can visualize that as a particular and effective. Okay, so if I say the zigzag angle is 85, that may correspond to particular and effective value. And at that and effective value, we've got particular values of d over lambda for the M equals 0, 1, and 2 modes that we're interested in. We're interested in the 0th and the 2nd mode. So basically what this problem is doing is calculating these d over lambda values, these two values, and of course, knowing lambda, 1.3 microns, we can find the d values that correspond to that. So that's what we're doing in this problem. And the basic technique is to draw these curves, draw this set of curves, and we know how to get the first curve, the M equals 0 curve. It comes from equation 4.11, which is the tangent of h d over 2, 4.11 I think it is called, is the square root of n1 squared sine squared theta minus n2 squared, and all of that divided by n1 cosine theta. Now, we saw that in order to make this mode plot in Excel, we could not solve for theta as a function of d by lambda. We couldn't do that. We had to solve for d over lambda, d by lambda in terms of theta, and that gave us these curves, or it gave us this first curve from this equation. So we're going to do that same move. We're going to solve for d over lambda. And we've done that before. I'll make a new page here to do that. D over lambda is given in terms of theta as the arctangent. And you can do this offline to solve this. That same square root divided by n1 cosine theta. And this whole arctangent is divided by pi n1 cosine theta. And that uses the fact, let's go back here, that h is defined as h is defined as 2 pi n1 cosine theta over lambda. Is 2 pi n1 cosine theta all over lambda. Hope you can read that. Okay, so plugging all this in and solving for d over lambda gives us this equation, okay, where the square root is that same big square root. Sorry, it doesn't look so great here. It looks pretty horrible, actually. And so what we can do is we can plug all the numbers in to this equation with n1 and theta given to us, and n2 also. And what we're going to get here is 2.49. So this is the d over lambda value for m equals 0. Because remember, this equation that we start with for this whole entire calculation just gives us the m equals 0 curve. Okay, and that implies, and so we're done basically with part A. We can solve for d, which is 2.49 lambda, which is 2.49 times 1.3 microns, which is 3.24 microns. Okay. The trick to part B now is to realize that the spacing, the horizontal spacing between these curves, is given by an equation that we call delta d over lambda. And we haven't dealt much with this equation in the problems in the form that it originally came in as 1 over 2 n1 cosine theta. Most of the time we deal with this equation, we deal with it evaluated at the critical angle, that is plugging in the critical angle, and we call it delta d over lambda critical. And that's this value that I tend to call delta on this horizontal axis. So that is the spacing down here all the way down at theta equals theta critical. But we're interested in the spacing up here where theta is equal to 85 degrees. And so we're simply going to plug in 85 degrees for this part of the calculation. 2 times 1.48 times the cosine of 85 degrees. And so this delta d over lambda value comes out to be I think it's 3.92. And so what we can do then to find the case m equals 2, we can say that d over lambda for m equals 2 is d over lambda for the case m equals 0, that's this one, the first one, plus twice delta d over lambda. And so this is going to be 2.49 plus twice 3.92. And that's going to give us if I've got this 3.92 correct here, let me fix up my 3.92. I just made it worse. Can I fit a 3 here? Is this legible? 3.92. This gives us 10.24. And so finally, D for this case is 10.24 times lambda, which comes out to be 13.32 micrometers. Okay, so that's the solution to this problem. And as I say, we're using this delta D over lambda value up at some other angle that's given rather than down at the critical angle. If we evaluate this equation at the critical angle, we get this spacing between the cutoff values, which is what most of the problems we've done ask for. But we're interested in this horizontal spacing up here at theta equals 85 degrees. So that's that.